Welcome and hello. This is a video tutorial in HEC RAS, and in this lesson, I'm going to be talking about bridge scour. Bridge scour is important because it is one of the leading causes of bridge failures worldwide. It refers to the erosion of and removal of sediment such as sand, gravel, rocks around the bridge abutments, piers, and foundations due to swiftly moving water. All right, what I have on the screen here is my HEC RAS, and I've got a model already built and ready to go. We can find the bridge scour in Run menu. You come down to Hydraulic Design Functions, and then here it is right here, bridge scour. This is the first hydraulic design calculator. If you click on Type, the Type menu here at the top, you can see bridge scour. That's the first one, so that's why it's selected by default. But there are a number of other hydraulic design calculators in HEC RAS, as you're seeing here: riprap, uniform flow, stable channel design, and so on. All right. So we're going to be talking about this dialog box for the majority of this lesson. But before we do, I just wanted to point out a couple other things about bridge scour and this particular model that I have set up. Also, you can access this hydraulic design dialog box directly from clicking the button right here. It says HD just left of the RAS mapper button. Boom. And there is the hydraulic design calculator once again. There are a couple important points I wanted to first mention about this bridge scour calculator in HEC RAS. First of all, it's meant for single events, like one large storm event, like a 100-year storm or flood, 500-year flood, and so on. It's not meant to calculate years and years worth of continuous degradation of soil from around the bridge. And then the second point I wanted to make, the user manual points out that HEC RAS was originally based on the 2001 version of the FHWA Hydraulic Engineering Circular 18, and that the bridge scour methods and calculations were based on that original 2001 document. Since that time, the FHWA has updated their bridge scour and all sorts of information, but the HEC RAS scour calculator that we're going to be looking up today has not been updated. These older bridge scour routines currently in HEC RAS were left in the program in order to reproduce previous studies that used this software. So it's not useless, but it's not as updated as it used to be. All right, so let me go ahead and show you the model real quick. We've got our river reach here from river station 0 upstream to river station 10,000. Here are the cross sections here. This is river station 10,000. This is river station 0, and it's just a linear interpolation up. I've already ran a simulation. We can do that again as well. Here is the bridge. So we have the deck roadway information right here, and then we have pier data right here. There's only one pier. Let me close that. And we have sloping abutments. This is the left and this is the right. So if you wanted to use my exact numbers, you should be able to pause the video and copy that if you want. Let's go ahead and run a unsteady flow simulation. I already have my hydraulic data. Here's a hydrograph. This is what the flow looks like. So we're going to see that in the channel. I click OK and then run and then compute. Okay, that looks fine. So I'll click close. Let's go ahead and take a look at the results quickly, just at the bridge cross section. So cross section, here is our bridge. It's at river station 4900. And then let me just go ahead and animate the flows real quick. Boom. So the water goes up and then back down. Let's get going with that scour information. HD. Now, if I wanted to create a new hydraulic design data, I could do that just by going File, New Hydraulic Design Data. I don't need to do that. In fact, I already have 3 examples of bridge scour I've been working on in preparation for this lesson. So I just created number 3. So this is all ready to go. At the top, we have the title of that hydraulic design file, as well as the river, the reach, and the river station. Of course, this is about bridges for bridge scour. So our only selection for river station is the river station with our bridge right here. It's about halfway up in the reach at river station 4900, and then that's just downstream of river station 5000. Let's see. Also, what we have here is the profile. So this water surface profile right here appears to be around 47 feet of elevation. That could be changed if I go ahead and change the profile to a different time period, as you're seeing. Okay. So I'll just go ahead and set it back to max water surface. And then over to the right, we have a few buttons. Defaults right here, if I click that, it will reset all the default values for the three tabs. The compute button will actually run the calculations and then update the diagram. And then the report will provide a report on the screen of those results. All right, so let's get going with our different tabs here. Over to the left column here, we have three tabs. There's contraction, and then pier and abutment. So these are the three different methods or mechanisms that bridge scour can occur. So contraction, for instance, this is erosion across the channel width caused by contraction of the river as it approaches the bridge. Next up is pier, right here. This is the erosion of the pier, localized erosion of sediment around a bridge pier caused by the turbulence and vortex formations at its base. And then the last tab here is abutment. This is erosion around the abutment, localized erosion of sediment around the abutment. There's a left abutment and a right abutment. And then I have only one pier for this particular bridge. Okay, so let's talk about the parameters in detail, starting with contraction. As you notice that there's a left overbank column, a main channel column, and a right overbank column. Right now, the water surface elevation for the entire simulation, in fact, never gets above the overbank, so I'm only going to see data for this main channel, not the left or right overbank. If you see the text already filled in like this in green, that means the data has already been taken from either the bridge data itself that I added and saved into the geometry file, or it's taken from the results of the simulation we just ran. So this 5.35 right here, this is the average depth at the approach section. So that's in the main channel. So if it was for the left overbank, this would be the left overbank average depth and then right overbank average depth. When it refers to the approach section, that's listed down here at the very bottom. I really think this cross section or this drop down should be higher up, but it's set to 6,000. This is River Station 6,000. So let me go ahead and zoom in. Oops. Okay, I'm zooming in on the map here. So what we have is the bridge right here at River Station 4,900. And then just upstream of the bridge is 5,000 cross section and then 6,000 cross section. It's this River Station 6,000 cross section that's being assigned as our approach cross section of River Station 6,000 as our approach cross section for the bridge. The approach cross section should be located at a point upstream of the bridge just before the flow begins to contract due to the constriction of the bridge opening. The program assumes that the second cross section upstream of the bridge is the approach cross section. If this is not the case, the user can select a different river station to be used as the approach cross section. So if you know that the contraction begins at say 300 feet upstream of the bridge and your bridge is at River Station 4,900, you can just add a cross section at that needed location. So 5,200, for instance. And once that's added in, you should be able to select it from the drop down here. Okay, let's get on with these parameters here. We talked about average depth. V1 is the velocity in the approach section. So that's the velocity here at River Station 6,000. And then Y0, this is 4.69. This is the average depth inside the bridge opening. Q2 is 4,419. That is the flow through the bridge opening. And by the way, you probably noticed that as I'm mousing over these different fields, I'm getting a label that's a little bit more helpful than just Q2. This one says channel flow through the bridge opening. And of course, this would be left overbank flow and right overbank flow. The problem is you don't see the units, but you can see the units if you go ahead and click. And then down here, it says channel flow through the bridge opening in CFS. And then if you wanted to know what Y0 is, you click on that. You get the title. Yeah, channel average depth inside the bridge. And then down here, it says channel average depth inside the bridge, and that's in units of feet. So if you're ever curious about the units, you can look down here. Why they aren't included right here, I mean, there's plenty of room for it. They probably should have done that. W2 right here, this is the top width inside the bridge opening for the main channel, and then also left and right overbank. And then D50, this is the grain size distribution of the material in the main channel. So just think of the particle size of the grain size distribution where 50% is finer. After that, we have the equation to use. So our options here are default, live, and clear. Live refers to live bed and clear refers to clear water. If you select default, which is the default selection, then HEC RAS will determine which of these two methods to use. It'll typically use live bed for higher velocities and clear water for lower velocities. The user's manual provides more information about what these exact parameters are and some of the details about which equation to use. If you select default or live bed, then you also need to specify some live bed specific data down here. That is Q1, which is the flow through the approach section. W1, just below it, that is the top width at the approach section. And then K1 is exponent that's used for live bed contraction equation. So this is something the user would have to type in themselves. But if you're not familiar with what that is, there's a special calculator that will do it for you. Go ahead and click on this K1 button. And it looks like I need to input a D50 value. So I'll just say 1 millimeter and then click on K1. All right. So this little dialog box came up for determining K1, where I can go ahead and put in the slope of the channel. No, this is the energy grade line slope. Yes, at the approach section, that's River Station 6000 in my case. We also have the shear velocity right here, this V asterisk. The shear velocity is a lot slower than the velocity up here at the approach channel. And that's because the shear velocity refers to the velocity of the flow as it's making contact with the erodible material, whether that's clay or sand or silt or gravel or aggregate. It's definitely going to be slower because of the friction. You know how that the velocity distribution with width gets a lot slower as you hit the walls, or in this case, the bottom of the channel. This shear velocity is sometimes called the friction velocity. Okay, next down is water temperature. This is something the user can type in. That's in Fahrenheit. Oh, look, we have units. So yeah, it's not that hard to label units. All right, but half of these parameters are unitless, such as the next one, the velocity over velocity. And then finally, K1.64 is the calculated K1 based on all of these parameters. So it's empty here, but if I click OK, it'll just populate to 0.64. All right, we got all the parameters in for our contraction tab. Let's move over to the Pier bridge scour parameters. At the top, we have a radio button to select either maximum velocity and depth or local velocity and depth. Now, this may be a little confusing with my example because I only have one pier, but if I had multiple piers, then this pier number right here, I could select the different piers and they're identified by their number. And then also the center line stationing, 175 is where this pier is centered on. But anyway, local would have different data for each pier, or I could just use maximum. So I'm going to use maximum, which means it applies maximum velocity and depth for each pier, which is sort of a conservative worst case scenario type of approximation. Below that, we have the shape of the pier. So you can select square nose, round nose, circular cylinder, and so on. As you change the shape, then that's also going to update the K1 coefficient and also the phi coefficient down here. So if I select something else, those numbers change. Maybe not. Okay, yeah, there they changed. We'll talk about those a little bit later. All right, next up is A. This is the pier width. This value is actually taken from the geometry data. So if I open up the bridge and then I open up pier, you can see the width is 12 feet, both upstream and downstream. Okay, let me close that back up. And then Y1, 5.48. This is the average channel depth of the approach section. And then V1 is the average velocity of the channel at the approach section as well. So I think this subscript 1 refers to the approach cross section, which is the same cross section we were talking about here in the contraction tab of 6,000. All right, back to the pier. D50, we've already talked about that. Froude number, that's just a calculation, not something we can change. After that, we have to specify, do we want to use the Colorado State equation or the Froelic's equation? Now, if we select Colorado State, we need to provide values here, and then Froelic's equations are disabled, and vice versa. If we select the Froelic's equation, Colorado State information is disabled, and we have to enter this data down here. Okay, so for Colorado State, we need a K1. This is a coefficient based on the shape. It's a correction factor for the pier nose shape. And then after that, Angle. This field is used to enter the angle of attack of the flow approaching the pier. If the flow direction upstream of the pier is perpendicular to the pier nose, then the angle is entered as 0. So I think that's the most common situation, or perhaps the water is approaching the nose slightly off by maybe, we'll just say 5% or degrees or radians. Who knows? There's no units. Yeah, there's no units down here either. I'm pretty sure it's degrees. The user manual does mention degrees, but it never explicitly states that's the unit of this field here. So as you can see, K2 is a coefficient that is based on that angle. I could change the number here, and then you'd see a different number for K2. I'm going to go ahead and leave it at 0. L, this is the length of the pier in the direction of flow. And again, that's coming from bridge here. Actually, I'm sorry, it's going to be in the deck roadway. Here's the width of the bridge, hence the width of the pier as well. Okay. Okay, we're back in K3 here. K3 is a correction factor based on the bed condition. So we're also selecting either clear water scour, plain bed, and anti-dunes. I'm not going to try to read all these, but you can see that there are different numbers associated for K3. Finally, we have D95. This is, again, that grain size distribution. It'll be a larger number than our D50 up here. So I'll just say 2 millimeters. This is the average grain size of the distribution, where 95% by mass is finer. And then K4 here is based on D50 and D95 sizes. It's used to decrease the scour depth based on pier armoring. All right, we have a couple parameters down here using Froehlich's equation. This phi value we already talked about, that's based on the shape of the pier. And then finally, A prime is the projected pier width with respect to the direction of flow. So yeah, if the angle here is 0, then the pier width would be the actual width of the pier, but it would probably be a little bit larger number if that approach angle is not 0. All right, we have one more tab to cover. That's the abutment tab. We have a left abutment and a right abutment, so your data may be similar on both sides. Unfortunately, with my example, the water doesn't get up to the abutment, so it's going to seem a little bit awkward in some situations. For instance, Y1 here, it's the length of the abutment and road embankment that is obstructing the flow. And it's really should be 0 because length can't be negative. But the reason why it's negative is because the water surface elevation is actually below the lowest elevation of the abutment. So we're going to have 0 bridge scour due to abutment for this particular simulation. But up here we have the tow station at the bridge, both the left and right side, as well as the tow station of the approach. That's the approach cross section. So we have 70 and 280, and you can just glean those numbers from the plot itself, because this river station is 50, here's 70, here's 100. It's talking about this 70 here, the little green arrow. And then on the right, we have 250, 280, and 300. So I tried to make this all symmetrical. K1 right here, this value represents a correction factor accounting for abutment shape. So if you select the abutment shape, it's just the few different options you have right there. Skew angle, it's default to 90 right here. This field is used to enter the angle of attack of the flow against the abutment. A value of 90 degrees, which is what it is here as default, should be entered for abutments that are perpendicular to the flow. And this is the normal situation. But for instance, if the abutment is pointing upstream, this angle will be greater than 90. And if it's pointing downstream, it'll be less than 90. After that, we have K2. This is a correction factor based on the skew angle. So it looks like that calculates automatically. Let me go ahead and change it to 80. Okay. If I change it to 70, I see how that works. Okay. I'm just going to put it back to 90 though. And as with Pier bridge scour, the abutment bridge scour also has a couple different options for an equation: default, Froehlich, and higher. Default would just let HEC RAS decide which of the other two methods to use, and then Froehlich and higher are those other two options. If it's a shorter length and deeper approach depth, it'll probably use higher. And the opposite is true if it's a longer length and shallower approach depth, Froehlich. The exact details of how it decides is also provided in the user's manual. So if we select Froehlich, we have some Froehlich data to input right here. L prime is 0 right now. This is the length of the abutment normal to the flow. This value is automatically computed by the program once the user enters an abutment length and a skew angle. After that, YA, the average depth of flow or hydraulic depth that is locked by the embankment at the approach cross section. I'm just reading the user's manual right now at this point. QE here is the flow obstructed by the abutment and embankment at the approach cross section. And finally, AE is the flow area that is obstructed by the abutment and embankment at the approach cross section. If you select higher as your method for abutment bridge scour, then the velocity at the toe of the abutment taken from the cross section just upstream of the bridge is the value required. Again, some of these values can be changed, some of them are locked in, and there's more information about what I just said in the user's manual for those who really want to dig in. All right, so we've made some changes here. I'm going to go back to the contraction tab, and to save, I'll just click this apply button near the top right. Boom, so that's saved. If I wanted to reset everything, I'd click this defaults button. I don't want to do that though. And then to compute, I'll just go ahead and click this button. And boom, we see a huge amount of bridge scour, specifically under the pier, it looks like. We also have a little bit of bridge scour here due to the contraction. And as you notice, there's no bridge scour due to the abutment. If we want to take a look at some of this data, we can click on the report button here. And then let me resize this. Okay, so I got it all on the same screen. Here is the contraction scour information up here. And then we have pier scour data right here, and then combined data. We don't have any section for embankment because there's no embankment bridge scour. But for each of these three sections or two sections, we have input data at the top and then results down below. Input data at the top, results down below. And we have the sum of the two depths right here for the main channel is 14.24 feet. Most of that is coming from the pier scour, 13.07 feet, and a little bit more coming from the contraction scour of 1.17 feet. Most of this data we saw because it was part of our data input, but the results data here is the new information in the report. With this report, we can copy it to our clipboard, print it, or save it as a file just by using these buttons down here at the bottom of the dialog box. Okay, I'm going to go ahead and close that and then see if I can make some changes to reduce the amount of scour and then run it, compute one more time, look at the report, and then we'll call that good. So let's focus on the pier bridge scour because that's where the 90+% of our scour took place. And one thing we could try doing is just eroding not sand or something 1 millimeter. We could increase the size of the D50 to say 50 millimeters, and the D90 could be say 120 millimeters. Okay, I'm not sure how much that's going to affect things, but let's click apply to save, and then I'll click the compute button. And just like that, you notice that the amount of pier bridge scour probably decreased by half of what it was originally. This appears to be like 6 or 7 feet, in addition to the already existing contraction bridge scour, which probably is still the same. So I'm going to click on the report once again. Now this time, yeah, we still have the same. This is contraction scour of 1.17 feet, but then now the pier bridge scour is only 5.23 feet. So it's less than half of what it was just by changing the material of the channel for a total of 6.4 feet. Still catastrophic. We still lost the bridge, but anyway, I'm not going to do any more in this lesson. We talked about bridge scour as a type of hydraulic design. We went through the 3 different tabs and then ran an example to determine how much scour would actually occur using our input data for this particular HEC RAS model.